All right, we are live now. I'm also going to start the cloud recording just in case, like, belts and suspenders. And Gaurav or Bhavesh, can you just kick off the meeting and then we can get started? Gaurav, you're on?
Yes, I'm there.
Just kick off the meeting and we get to good to start.
Okay. So hello everyone. I'm Gaurav from SDE Skills, and now we are running this meetup, in-person meetup, like on the east side for almost 7 to 8 years, or even over that. And yeah, like there will be like noise like on my side. Like, do you want to take it? Because my son is around.
No worries. Let me do that. Okay. So, hey, welcome everyone. Um, just wanted to have a very quick kickoff for this one. So we've been trying this new format for online meetup. We've been doing in-person meetups for almost like 8-9 years, as Gaurav was saying. Let's actually get, without too much ado, let's get going. Martino, do you want to quickly introduce yourself and then talk about, and then take it from there?
Hi, so yeah, my name is Martin Nikolsky. You might know me from the live meetups that we had previously. I've been in this group for a couple of months now. In the beginning, I wasn't attending that frequently, but recently I've been try to go as much as I can. I try to keep my skills sharp and improve my algorithmic and also data structure skills. So if you plan to do the same, I think this is the perfect place and group to be in. I'm gonna start with I hope you had time to actually go through the problems. So we're gonna start with question 1, find the town judge. Okay, so in a town there are n people labeled from 1 to n. So we have, let's say, we have, okay, n people. Okay, this is label 1, 2, and then n people in this town. And there's a rumor that one of these people is secretly the town judge. So if the town judge exists, so means that the town might not have a town judge, then the town judge trusts nobody. So let's make this town judge this guy. Okay, let he be number 5. So everybody except the town judge trusts the town judge. So these people are everybody else but the town judge. So they all trust him. Okay. And then there is exactly one person that satisfies property 1 and 2, which is the town judge. So you're given a trust, an array of pairs, trust of I. So you're given an array. Okay. Of pairs of trust. This is trust. Representing that the person labeled trust a person labeled A trusts the person labeled B. So if the town judge exists and can be identified, return the label of the town judge. Otherwise, return -1. So meaning that, okay, this array is gonna have actually a subarray. Let's do it again. So it's gonna be my pen. Let me start over this. So we actually have an array of arrays. Okay, so 1 trusts 2, then 1 trusts, I'm sorry, 2 trusts 3. Let's go through the examples. We can give more later on. So the first example is actually the town has 2 people. So 1 trusts 2. So this is clearly the town judge is 2 because 2 doesn't trust anyone else, but 1 trusts a 2. The example 2, let's say we have person number 1 trusts 3, and also 2 trusts 3. So this clearly makes 3 the town judge. Example 3, for example, we have 1 trusts 3, and then 2 trusts 3. But 3 also trusts 1. So this means that it doesn't satisfy the condition that the town judge trusts nobody. So this means that the town judge, this town has no town judge. Any questions so far?
Looks like no.
Okay. All right. So can somebody tell me how would you solve this? Anybody?
We can calculate in degree and out degree.
Okay.
And so town judge should have like n-1 in degree, but 0 out degree.
Okay, cool. You wanna start telling us, I mean, write it, or you wanna take over?
So what do we do here? We code it or try to explain it, because you have already explained it, I guess.
Yeah. So we can start. Are you comfortable writing it here?
Yeah, I can write. How can I write? Should I share my screen here?
You can either share your screen, or you can I can give you remote control.
Sure.
What was your name? Roger, right?
Roger, yeah.
Okay. Yeah, I think you have control right now.
Okay.
If you don't mind, you can also say how you walk us through the steps.
Yeah, sure. I'm just trying to learn how I would write, because I can't see
Okay,
my.
I'm gonna zoom in.
Yeah, that would help.
Okay, there it is.
Yeah. So as we just talked about, this problem is, so town judges, everybody trusts town judges, and there are n people. So if we can create think it like a directed graph, like, A knows B. So everybody will be having a pointer towards the town judge. And so by definition, we need to have n-1 pointers towards the town judge, and that I'm talking about, like that I can call, it's in degree towards that person's node. But also the other thing is that town judge should not trust anyone, so there should be 0 out degree, anything going out from there. So that's the approach I would go with. If there is any question, I can answer, or I can start coding it. Yeah, I think I should start coding. So what should be the function name?
The function name, okay. The function name is find judge.
Okay.
So it returns an integer.
Okay, let me see. Find judge.
Yeah, and then it takes an integer n, capital N. It doesn't matter actually.
Okay,
and then and we have
two-dimensional array.
Yeah, I'll trust.
Okay, that's it. And you have n also, like how many people are there?
Integer n, correct.
Okay.
Okay.
Okay. All right, so let's do one thing. Result equal to -1. Let's return this. Yeah. So after this, like, okay, I want to create two thing, in degree and out degree. And there are n persons here. So what
Okay.
I want to have two arrays, like call it degree uint array with n persons. Similarly, we will have out degree. All right. So now we'll go for, like, we'll go through this trust array for each relationship. We'll build these like this two value. Okay. So for int equal to 0, actually for, let's call it for int. Okay, it's already called trusts. Let me make its name trusts, and let's make this trust.
Yeah.
Okay. So now we have one trust, and for each trust we are going to populate this. So in degree of so the first value means like one trusts two. Okay, so what does that
Yeah.
mean? That one trust two, that means okay, in degree of the second should increase. So in degree of trust one should be increased, right? And out degree of first. So out degree for one should increase. So out degree of 0 should increase, right? Okay, so at this point of time, like, we'll finish this and then we will check like uh, if we have a solution or not. So we'll just check that. So again, let's go through each of these guys, right? Okay, so how many people we have? We have n persons. So okay.
So what are we trying to find here right now?
So at this point, you can have, like, you have, maybe you have no solution, but you may
Mhm.
have solution. So now you are checking that, okay, did I find any person for which in degree is 0 and out degree is n-1, right?
Got it. Mhm.
Yeah, because if it is, then we can return the result. Otherwise, we will return -1. So for all of these, like, possible candidates, basically, we'll check, hey, if in degree for any of this guy is okay, 0, and out degree for the same guy is equal to, then result equal to this value. So I,
Okay.
and if not, and actually you can break at this point of time also.
Awesome. That's gonna
Yeah,
improve actually.
yeah. So let's see, will this work for this problem? So n equal to 2, trust is 1 to 2. You are
Yeah.
outputting 2.
Yeah, we
So
can
yeah,
actually kind of like draw maybe um like a table where On the left side, you have all the nodes, and on the right side, you have in degree and out degree. So it's like more visual as we go. You know what I mean?
Oh, you want me to draw something here?
Yeah, we can, for example, like this. We can have a table. Let's go, which example you want to try?
Yeah, I can build something. Let's try something. Maybe fourth example is maybe the best, maybe. Let's try
Okay.
that.
Okay, I'm just gonna draw like here. So we have, here we have the person,
Mhm.
and we have how many? 4, right? So 1, 2, 3, 4, right? And we have in degree, okay, and we have out degree. Yeah, so you can take over.
Okay. So 1, 2, 3. So that means in degree for 3 will increase. So we'll have 1. I can't type anything here.
I'm sorry, here, here.
Okay. Oh, okay. I have to write down. Okay. I was trying my pen. Sorry. So let's
Oh,
see.
you have a pen? Okay, so you can try a pen. Yeah, no problem. Here, pen.
Yeah, I'm still learning this thing. I have never used it.
Yeah, I actually got myself too, so trying
Yeah.
to get used to it. Yeah, you can
Okay.
take over with pen.
Yeah, let's see. So 3. So in degree for 3 should increase here. So we'll have 1. Okay. Okay. For some reason. Okay. We'll learn it later. So let's make it 1 for now. And this out degree for 1 was here, like, to begin with. After the first, array, we just, after the first trust array. So then we have 1 to 4. So out degree for 2 will increase and 4 will increase. The in degree will increase here 1, right? Then we
Yeah.
are having 2, 3. So for 2, out degree will increase by 1. So this will be like this, and 3 will become 1 plus 1. Okay. Then we have 2, 4. So 2, 4 means out degree is this for 1 plus 1. And then 4, 3. So 4, 3 is 1, and then 3. So in degree will be here plus 1. We'll have these values, and now we will check for each person the in degree and out degree, whether anyone has the in degree 3 but out degree 0. So as you can see that person number 3 has that value, right? Because in
Correct.
degree is 3 and out degree is 0. So that is how it will work.
Cool. Thanks, Roger.
Thank you.
So any questions about this? Any unclear?
So can we combine the 2 for loops into like one pass through the trusts array?
Yeah, you want to try it? See how?
Sure, yeah.
Yeah,
Yeah, I'll
take
give you.
control.
So I'm gonna give you. Who wanted to try?
It's Hanif.
Hanif. There you go. You can control now.
Okay.
There are a
So
few
yeah.
quick, before Hanif, before you just jump in, there are a few quick questions on the chat. I just spotted it. One is like
yeah.
how to check criteria number 3, that there is exactly one person satisfying criteria 1 and 2. This is for Roger.
Yeah, so the question is how, so there is exactly one person that satisfies. Okay. That's a good thing. Actually, I missed that part. So in that case, I wouldn't break and I will add a count there. Like if there is anyone who, but also actually one more thing. if there are two persons, it may not work, because then you will never have n-1 value for a trust, because if there are two such values, you will have n-2 at the most, like n-2 persons which are trusting you. Does that make sense? Whoever asked this question, suppose there are 10 persons, and you think like there will be two such town judges, who qualify to be town judges. Actually, the person who qualifies will need 9 persons to trust him, right?
We can
And
actually draw that out. I'm sorry. Do you have an idea how to?
So just one quick comment. I think condition number 1, 2, 3, all of them are like part of problem and they are given. So they will be valid, at least in this, for this problem.
yeah, it is possible, but even if it is not, then there will be no town judge. If you think there are two such, no 2 person can have this,
Exactly. Yep.
1 and 2. It's not possible.
No, actually, the question very clearly says that if a town judge exists and can be identified, then return the label, otherwise return -1. So it is quite likely that you may have no town judges at all. So the specific thing that Anand was talking about is a scenario where what if it's not just one unique person, but there are like multiple people that that satisfies property 1 and 2. So they're actually, it's impossible, right? Because
Right.
if there are two people where that trusts nobody, then the number of people who trust X or Y or Z can at most be n-2, right? Because
Right.
X and Y do not trust anyone. So there is no way you'll have an n-1 in the trust flag that you're talking
So I
about.
think he was talking about in this case. So 1 to 3, and then 2 to 3. So 1 trust 3, 2 trust 3, but also 1 trust 4 and 2 trust 4. Correct? Is that the scenario he was talking about?
So who are the ones who don't trust anyone? It's 3 and 4, right?
Yeah, 3 and 4. So their
And-
in degree is gonna be actually less than n, so it's gonna satisfy. So
Yeah.
there's no town judge.
Yeah.
That's how it will work. Good.
Right.
Good.
So I have one question. In the previous example, the answer is 3, right? The one Roger drew the table.
Yeah.
So I just want to check that condition. If it should be the in degree I is equal to n-1 and out degree I is equal to 0, where you are taking the answer. Yes, yeah, that line in the for loop.
Oh.
The
Yes.
if condition.
Right.
Because
So-
Yes, you're right. Yeah. It should be switched. Right. So town judge, actually in degree should be n-1 and out degree should be 0. If somebody can control that, you can fix that bug in the second for loop.
yeah, over here, right?
Yeah, in
So,
degree. Yeah. Oh, no.
And also in the first
Which one?
for loop, do we have to do -1 because the trust, the index is
yeah,
starting-
yeah, it should either -1 or you can add +1 here, and we'll have 1 extra one. Okay, so let's do here.
So wait a minute. What I'm
No,
saying?
no, I think the only change needed is the second for loop. That's
For
it.
loop, or you can give control to me, I can change it.
Not really. I think also it needs to be done here too, because when we get the trust 1, it might be 1. It can't be. It never be 0. So the in degree, the 0, the first element is not going to be ever populated if we don't put -1 here.
So my for loop is not index based there, if you look at it. Right? So
Okay, so the way to fix this is probably we can add +1
See,
here,
actually
Yeah.
I got it, what you are saying. Okay.
+1, and we can do start from 1 here, and
Yeah,
that will be good.
and still we have to fix the if condition.
Well, this one?
Yeah,
Okay, what
Yeah.
would you?
it would be if in degree I is equal to n,
Basically switch
Oh.
the in degree and
Switch,
out
yeah.
degree.
Okay.
One more thing is that if you are doing this, the for loop should run for I less or equal to n or I less than n plus 1.
I think less than equal to n.
You're right.
So
The reason why is because they don't start with 0, they start with 1. And if we have 4 people, then the last one is going to be 4. So
I mean, it can start with 0. It doesn't matter. It's just that we have to make sure that we basically go through all that.
yeah, changes. True. Okay. So any other questions?
Okay, maybe I'm missing this. So if in the last iteration of the loop, when I is actually n, it should work because you've defined the size as int n plus 1, right? So it should be fine. The above the your
Where?
array actually runs even though it's 0 base, you're actually running from you're using all the way up to n. So it makes sense. Good to
Yeah.
go.
So the result should be, should be like result is equal to I or I plus 1?
Result should be actually I.
Just
Yeah, now it should be I.
Yes.
Yeah.
Okay.
I think this was tricky because all given input are 1 base. So while coding, we have to.
Yeah, and we're all like used to the 0
0 base.
index.
Yeah.
Cool. All right. So if there are no other questions, we can go through the second one. Any other questions?
Just like, one question is like,
Mhm.
is there any other solution like people can think of like other than this, like just for idea's sake?
I
I
think we don't need the 2 arrays. We can just go with 1 array as well. So
okay.
basically we don't need so in one place we are just adding, and then the same way for out degree just subtracting.
Okay. So, yeah, that's a good idea. So for example, 1 is gonna be at the end is gonna be -2, and for 2 is gonna be also -2, and for 3 is gonna be 3.
So
Right?
at one place the in degree would be n minus 1. That's correct, but yeah, that's what we want to check. So if you just make that under that line in degree trust I, where we are doing +1, change that out degree array to in degree only.
Okay. You want to show us real quick, or?
I think there would be a problem. Let's take the example where there is a problem and see if it works. The reason is that what if the 3 trust someone and
So then 3 cannot be answered.
I see.
Yeah,
So,
because it's going to be less than actually n minus 1.
So as soon as it trusts someone, its value will get reduced.
yeah.
So yeah, if here is like a 1, then it's going to be 3 minus 1, and that's going to be 2. So it's not equal to n minus 1. Yeah, it's probably a good solution too. Better.
Yeah, so there are like a couple of concerns I generally have, like, we're trusting the input a lot here. If there are like, duplicate edges that are actually described, then this code will not work, right? Because we are not like, for whatever it is worth, if they said like 1 trust 2, and then again they come back and say 1 trust 2 again, then we will actually have issues with that because we're just simply counting without checking for that. So you're making a lot of assumptions on the purity of the input, which is reasonable in an interview, but that is something to always be, worried about as to what could go wrong. That is one. The other approach that I was thinking in my mind was essentially, I would make I'll put every judge in a set and say that these judges, these are like, potential judges. And then every time I find someone who's trusting somebody else, the person who is trusting, right, is no longer a candidate. So I'm just going to go remove that person from the set. So at the end of this loop, I should only have exactly 1 element left. If I have multiple elements left, then there are no judges. If I have an empty set, then there are no judges. If I have exactly 1, then I will probably go back and check if this person actually trusts anyone. And in there should be only one. I mean, sorry, I would check if this person is trusted by everyone, which is another loop through the process. So there'll be two loops, but it'll still get the job done. Same O of n, both in terms of space and time.
Got it. So that's when we're not trusting actually the input. It's better to use that set to have a potential judge and then return it.
Correct. That one is actually not susceptible to this error I talked about.
Got it. All right.
Not necessary to do it that way, but it's good. And actually, Anat was asking about space and time complexity. So we just talked about it as well. Cool.
Cool. So we can go to the question 2, or talk about time and space. You said.
No, let's go to question 2. In the interest of time, let's go to question 2. I think we are about 35 minutes in, so let's do Q2.
Okay. All right. And if we have some time, maybe we can come back and just analyze it further. Okay, so question number 2 is, let's say equations are given in a format A divided by B is equal to K, where A and B are variables represented as strings, and K is a real number, floating point number. Given some queries, return the answer. If the answer does not exist, return -1. So we have A dividing B, right? We can think of it this way, is equal to 2.0. And then we have 2.0. And then we have B dividing C, and that's 3.0. So this is given. Now the queries are, is what's A divided by C? And what's B divided by A? What's A divided by, let's say, E here? It's A divided by E, or A divided by A, and X divided by X. So, but you can also know that actually when A divides by E, E does not exist in this graph. Here's the example. A and AB, BC, okay, 2 and 3. So the queries, we have the query. So this is the actual input, how it looks like. The input is always valid, so we don't need to consider. I mean, it's a good practice to actually make sure that the input is, never trust the input, but let's assume that the input is valid. Also, you may assume that the evaluating the queries will result in no division by 0, and there is no contradiction. Okay, which are also one of the things that we need to consider when evaluating the queries. And in this case, we don't need to. Does anybody have any idea how to approach this?
Yeah, seems like this is again, as you drew, it looks like a graph where the answer is between A to B, 2.0 is a weight, and B to C, again, 3.0 is weight. If I look the answer, it looks like if I want to have from A to C, basically I want to do from I can do like a DFS from A to B, what is the answer, 2.0, and then B to C, 3.0, and then I get 6 if I multiply them.
Okay. Yeah, that's shortly how it is. So can you cover other cases?
So it seems like if we have something like a thing like if I want to find a query BA, the answer should be 0.5. So basically we need to get the other part also. For if weight from A to B is 2.0, then B to 8 it would be 1/2 or 0.5.
Okay.
Yeah, and the same for, so basically we have to account both the sides.
Okay, this is 1 over 3.0.
If somebody asks me answer from C to A, so the answer would be 1 divided by 1.3 into, so basically it would be 1/6.
Okay.
There shouldn't be any cycles in the graph too, right?
No, it's not. It's not about cycles. It's
If there was
about.
if there was a C to A direct link, then there'll be confusion like which paths to take.
Yeah, there should not be two paths, or yeah.
Is that fine as long as like it's consistent, like you get the same answer regardless of which branch you take?
If there is a cycle also, it is fine as long as it satisfies the same condition basically. If you connect A to C, and if the value is same as coming from ABC and CBA, then it's fine.
Yeah.
Yeah, though
Yeah.
computationally, you'll have to figure out, you'll have to keep tracking which path you've taken so you don't take the same path again.
Yeah.
Mhm.
Okay, so somebody want to take over and how guide us through the solution of the problem?
I can try.
Okay. Sure. And who's that?
Asim.
Asim. Okay.
So you want me to like go through something like a pseudo code, or explain what I want to do?
You can start explaining as you code, or if it's easier for you, you can explain us first and then guide us through the code. And also
Sure.
we can actually also talk about space and time complexity, because it was requested, and it's a good practice to do that. We forgot about the first one, but we'll cover it later if we have time. So
Sure. So as we have seen, this is a kind of we have to come up with some data structure where I can put something like a graph, and graph should also have something like weights involved. So anybody wants to suggest what kind of data structure should I take, which will suit my requirements? Otherwise, I'll propose.
Maybe an adjacency matrix, like a 2D array.
Yeah, right now I can even go with like something like a map, where my key will be the start node, and the value would be all its children. Here, its children is only B, and like I mentioned, I'm also interested in weights. So if I'm putting B, I also want to put 2.0. So basically from A to B, it's a 2.0. And similarly, like I'm also interested in B also. So what is if I want to go from B to A, it would be like A comma 1 divided by 2.0. And similarly, B has one more connected children, which is like C. So I can just put C is 3.0. And then I need one more thing. Can somebody point me that? So if I'm going from A to C, I have to also put from C to B, which would be 1 divided by 3.0. So till now, is it clear?
So what's the advantage of doing it this way instead of like, let's say like a 2D array? Because wouldn't you have to search through the entire list to search for like one particular relationship?
Mm-hmm. So like a 2D array, you are telling like that adjacency that matrix thing?
Yes, yes.
So basically, we can try that, but I generally use with the adjacency list, where every node would have its own. I think there I have to make a 2D array and have a component between, have to put something like for A to B, what is the relation, and from B to, like, I have to construct a really, I think I have to consider all 26 characters, correct? So it would be 26 by 26 matrix.
So it's you're saying that it's gonna take more space than having
I think
map.
if the argument is between adjacency list and what is the other one?
Matrix.
Yeah. So if it is a dense graph, then 2D array is and adjacency matrix is good. Otherwise, if it is a sparse graph, then this is much better. But it is just representation of the graph. It doesn't matter what way we represent right now, because we really don't know the data. But I think we have to apply algorithms on both of that, right? It's just representation of the graph. It is not going to give us that answer. Yes.
Correct. So basically, any way we represent, it won't give answer till we start doing some kind of traversal on top of it. It could be a BFS or a DFS.
Yeah, I think there's no wrong or right answer here. That the adjacency matrix will help if we are saying that we are going to fill the whole array before even starting the answer. Basically, given a graph, we are going to fill the whole array.
Right, but like, could it have a difference in the time complexity? Like, let's say A had a huge number of outgoing edges, right? And I wanted to see like the relationship between A to Z. So then I would have to like index, I would have to search through the entire list, right, of all of A's neighbors to find the one I'm looking for.
Yes. So the answer to this question, and if I think what we are saying is that I will have a adjacency matrix. I will calculate from all node to all node distance, and then when somebody asks, I'll just give, right?
Yes.
Or other way is that I will just calculate whatever is asked. Say that A to C, nobody is going to ask me. I'm not going to calculate.
I see.
Right.
Right.
So both way it is fine. I think I'm not sure what. Okay, so I will just leave it to I mean, I'm not sure what algorithm we are going to use, but it might make some difference because there are algorithm in the graphs that says that from all point to all point, or there is an algorithm that just give the distance between 2 points. So it's depend on what we are using, but it's just saying that I'm gonna. So if we have suppose 10 nodes, we say that we calculate 100, whereas somebody is asking only us 10 as an output. Or will I calculate only 10 that is asked, and I'll calculate when it is asked. And I think both are same. Maybe it might depend on how many queries we are doing and a lot of other stuff.
Okay, sure.
Okay, so I will proceed with this adjacency list where for every given node, I can quickly iterate all its neighboring nodes. And I don't know how to, if it is a matrix, I might end up going to each column and find if there is a connection or not. That's what I'm not sure. So yeah, so this is what I was thinking. If we have a conclusion, then we'll proceed further.
Yeah, I think we can start with this, and then probably we can come back after we have a clear algorithm. We can come back and revisit this. Yeah.
Okay, sounds good. So basically, if I have a query, something like so this list is done. Now I want to find a query between let's say A divided by C. So if I start start a traversal from if I just start a traversal from A I can go to B, and from B I can go to C, and that is the end I'm looking for. Then while coming back from B to C, the answer the weight was 3.0, and then from A to B it was 2.0, and that will give me answer 6.0. So this is what I was thinking. Yeah, and if I let's think about a situation where I couldn't able to get the answer, like we have something like A2 A to D. So I could start with A. I went to B. From B, I went to C. From C, I can again come back to B, but that is already visited. So I would not come back, and then I can't go further. So that means I couldn't get any particular answer from this. And then I would start returning something like, let's say, some false or something. So I couldn't get the answer. And if I'm getting, or I can return something like -1. So basically I can keep on returning -1, and then if I couldn't get answer, and then I'll store -1 in my result. That's what I was thinking.
Is it clear, guys? Do you have questions?
One quick question. So, are you thinking to do DFS and keep calculating the value, resultant value, while you go deep into the graph? And if you don't find the destination node, then you backtrack the value and keep searching.
So yeah, so there are two ways. That's a good question. Either you first put in your result, and if you couldn't get answer, remove it. But I'll say do in a different way. If you could go really deep enough to like the end node, which is D, then only start putting it as part of your result. So you don't need to backtrack or remove it. So basically, once I so let's say there was a D in my path so if I am able to reach C, it will return 3.0 back, and which will get multiplied to A and B result, which will become 6, rather than first I take a result variable. So what you are saying, like first I'll take a result variable, which is 3.0. Then I'll pass it to the next level. It will add 2.0. If I couldn't get answer, I'll start removing 2.0. And then if I'll start removing 3.0. But what I'm telling, like doing the other way. So you don't have to remove. If you get a result, then only start compiling and sending it back.
Sure. Okay, got it.
Like there are some problems, tree problems, where we go to the leaf, and from there we start returning value, rather than the root is sending a value to its children.
Okay, thanks.
Otherwise, I need to do some kind of a backtrack thing, and I think we can avoid in this kind of problems. That would be extra logic to first put it as part of the result, and then if you couldn't get the right thing, and then remove. So might not be needed here.
So Asim, so DFS is the way to go, is it, for this? That is like.
That's what I'm thinking. Like DFS would be a good approach. I'm just trying to kind of a debate in my mind, like between DF and BFS. BFS is I want to visit all my children together, and then again keep on visiting. Here there is some element of backtracking. If some element, like if I couldn't get that answer in that path, then I'll go to a different path. So I think DFS is a good approach, but could be solved with BFS also.
And you were mentioning about returning -1. I don't think. I mean, what if A divided by B was -1? The weights themselves could be that value, right? So probably we shouldn't return like integer min, or I don't know, integer max or something like that.
Yes, we can even return, but if it is a weight itself is -1. They're expecting to put -1 if you couldn't get anything.
Oh, okay, okay. The return, okay, okay.
Yeah, it's included in the problem. If the answer
Okay.
does not exist, return -1.1.
Yeah, so they won't try to. I don't think don't try to match it with input. Like input could also be -1 because they're expecting -1 if nothing is there.
But
Okay,
they
and
say k is a real number, so yeah. But yeah, it makes sense. I think what if I missed that part, return -1.
Mhm.
And another thing to add in the meantime, we missed one case where it's a divided by a, so they could always be 1.0. So we should also include that in when we're building this matrix.
I don't think so. They will mention that otherwise. If you see, there is a query. Oh yeah, you're right. If it is a by a, it is 1, correct?
Yeah, so we're just gonna add any here like a to be 1.0 and also here be 1.0 and C is 1.0. Yeah.
Do you really need to store that though? Like, can't you just have a condition where if the
Yeah,
We can do that too. Yeah, we don't have to take the space. I mean, if we are going with that, it was Hanif, right?
Yeah.
If we're going with the matrix, it won't matter anyways, storing it or not.
Yeah.
But I guess here in this case, it might matter. So it's up to you. It's an option. Yeah. So.
And Asim, how did you build this adjacency matrix? I mean, what did you do to build it? So you just picked every node and looked at all its children. Is that what you did?
yes. Yeah, but again, this is not matrix. This is adjacency list.
Sorry, yeah,
Just want to
adjacency
clarify.
list. Yeah.
Yes, so based on the queries, what is mentioned, we given A divided by B. And actually, they have given the queries in the way, what is the input type? Let's see once. Okay, so they have given the queries.
They're given the edges actually.
Yeah, let me maybe zoom it in a little bit.
Yeah.
List of edges.
Okay, so there are two things. So we have already given A to C, which is 2.0. And we know C to A would be 1 divided by 2.0. Yes, so we have two different arrays, which they will give values and queries.
Maybe we can start with the code.
Oh, sure.
Because of time, we're kind of running out. Try to cover.
Seems code would be pretty lengthy, so let's get started. Okay. So what is? I'll just copy the input. So this is, I think, they have given us the queries, and then, like I mentioned, I will create a map. So I'm using Java. And then it would be a map of string double. Generally, let me put it in a different function where I will just get this map. And then I will pass my I will pass.
So we try to build the graph now, right?
Yeah, so I'm just trying to build the graph, and I will pass this. I have a code for that. I'm trying to find that. So let me copy paste the code here so it will make things really fast.
Okay, let's just go through it.
So basically what we are doing is we have a map where we have a new hash. We are just creating we are going through all the equations. And for that equation, I'm trying to find if that is already there. For example, this will represent A, and this will represent B. If it is not there, it will create an entry in the map, and
Okay.
and that will put item one dot put. It will put the value as it is. It will put.
So you're actually saying we're going from we're going direction A to B. We store the value, and when we go from B to A, we store 1 over the value.
Yes. So here, what
Okay.
it will do, it will put. For A, it will put a combination of B and it will put 2.0. And for B, it will also put A and 1 divided by, or let me put as 0.5 itself. And then we have to put again in the original map. So this entire item will go. Oh, sorry, my bad. It was like just confused myself. Okay, so what is So here we have some. So when we're doing for the first time, this will give me like an empty map here for A, and this will give me empty map for B, because nothing. We have never put anything there, correct?
Right.
And then I will say for A, just put 2.0, and for so what we are doing here is yeah, we're just saying for A, and then again putting, yes, so then again in the original map we are putting for A. So basically this is this thing we did here. We just put it B's for 2.0 and then.
Is that clear?
And then for A, I'm just putting back this, whatever we have put, basically we are just putting that item back in the map. We just don't lose it. So that's what it is doing. Is it clear? So basically we're putting, for A, we are putting that, this map back into the parent map. Is it clear?
Does anybody have any questions so far? How we build a map and any clarification?
I think it's clear. Yeah.
Okay.
Okay, cool then.
So after we build the map, what do we
So
need to do?
one quick question. If you come across another equation where A by E, let's say a different element, how will you accommodate that here?
A by E. So
Yeah.
So let's say what is in my map right now. Let me put it here. In A, I already have another map of B 2.0.
Yeah.
And then I have a B, which is having A, which is 0.5.
Yeah.
Correct. Now I get A and E. So rather than getting empty here, it will give me B 2.0.
Okay, got
And
it.
then for E, because it is never there in that, so get or default will give
I
me
see.
an empty thing.
Okay, so first time I'll give you empty, second time it's going to give you the...
Yeah, and what I'm doing, B 2.0 will remain there, but addition to that, I will also put C, something like this.
Okay.
And for E, it would be end up like 1 divided by 3.0. And then again, that guy I'm putting back, which was like, so is that clear?
Yeah.
But in this case, we don't. The only numbers we have is the A, B, and C. So E is not going to be here.
Yes. So I think that was just a question.
Yeah.
Got it.
So finally, my thing will look like this. So here A would have both of them. And there will be another entry for E also.
Sure.
Towards A. Yeah. All right.
Okay.
So
let's proceed further. Okay, so this part is done. And here I will just do like, I will say it map equal to get graph and just put here equations and values. Okay, so now I will start iterating through my queries. And before that, I'll also take my result set, which would be double of result is equal to queries. So basically, every query will have its own result here. And then I'll start going through each query. And I'll break that thing. Dot get I, and then I will have something like my start would be query 0, and my end would be query dot. Then I also so if my so now I'll say if my map contains key, which is both start map dot contains key. So if we both have start and end, so that means we can do some kind of traversal here. And otherwise, if you don't have both start and end, then there is no answer I can get it out of here. So, okay, so now our main component is this guy, which we want to play with, where basically the DFS and other things will come into picture. To do that, I will also take one set, which will tell me things which I've already visited, so I don't overdo things. And then we'll do a DFS over here. So for my DFS thing, I will pass my map, which is my graph. I will pass my visited and also pass my start and end. So let me put this DFS function also. I have that handy. It will save time.
Any questions so far? Is everything clear regarding this?
चष्मा बघ माझा.
No questions?
Well, just if we can just add optimization if start and end are the same, and we don't need to do DFS.
Which one?
If the value of start and end is the same.
Oh yeah.
Like 8.
Yes, we can. Yeah, we can. No, but it has. Yeah, we can skip that part here.
So can't you check that outside the for loop? Or I mean, outside the other if condition?
No, because I want that to be in the map also. If you see that example XX query, it should be -1. So technically, it should be in the map.
Oh, okay. Okay.
Yeah.
So what we are saying. Okay.
So we are saying that if it is not in the map, then that node to same node distance is what? -1.
Yeah. That's what the question says.
Okay.
If you see, there's a query X by X. Yeah.
Yeah, it is -1.
I think I can move this.
Yeah, I can see that it is -1, the last one.
Yes.
Yeah, makes sense.
Okay, let's do a DFS here. What we are finding out here is as soon as I will make that visited, then I'll take all its children, and over here, if the children are not null, then I'll start taking one at a time. The next one would be my new start. But if the new start is actually equal to end, I just need to return the value over here. That's it. If not, then I'll go one level deep and do another kind of DFS. And And if I couldn't find anything, I could return -1 and then also look for -1 here. If I not got a -1, and then I'll just whatever the result which I've received from the below, I'll just add my value and return it.
Any questions? Something to be clarified, or concerns, or improvements?
So we are done with this, right now. Whatever
Yes.
the same- Okay. So just to add on this, okay. So this is perfect solution. But if you just want to know the specialized algorithm, so basically any method like DFS or we have a Dijkstra algorithm, right? Those are algorithms to find distance between one node to all other node. Specialized for that, right? Now there is also specialized algorithm, just for the sake of knowledge, that basically find the distance between all node to all node. There are two algorithms. One is Floyd and one is Johnson's algorithm. Basically one is optimized for a dense graph. One is optimized for sparse graph, because both complexity is different. I'm not expecting anyone to, suppose in interview write that, but if you know that, we can directly use that algorithm. That is a little bit optimized than what we are doing here.
Okay, so let's say we just know how many nodes are in the graph. We can actually determine the number of nodes, which way to go, correct?
For example, Floyd algorithm has a complexity of a number of vertex. So it's a V cube, and the Johnson's algorithm has a complexity of V square log of V and E edges. So the edges will control Johnson's algorithm. So if there are like less edges and more vertex, then the Johnson's algorithm is good. If there are dense graphs, so that edges also more close to the vertex, then the Johnson's algorithm is good. Oh, sorry, Floyd algorithm is good. But those are specialized algorithm. I am just sharing that just to know.
Johnson and Floyd, right?
Yeah, Johnson Floyd algorithm. One is Floyd and another one is Johnson's algorithm. You can search using Floyd algorithm.
Floyd Warshall, right? That's the one.
Yeah.
Okay,
yes.
got it.
Yeah,
it's good to know.
Yeah.
Write it down, take a look.
Mhm.
Well, thanks for that information.
So, and I think they have constraint of negative weights also. In this case, there is no negative weight. So I don't remember, but yes, there is constraint of negative weight also.
Yes, that's true. Not negative, basically negative cycle, and that represent negative weight, I believe, but I think negative cycle.
Yeah. Don't remember.
Okay, now with this algorithm, I think we should always discuss about the time and space complexity. I mean, at least.
With it, okay.
Yeah. I mean, with any of our solutions, right? So if we can quickly discuss that.
Here, actually, the worst case would be like for every query, we would be traversing all the nodes. So it would be like number of queries and into number of nodes, what I'll say. Like if in the worst case. So in the other example, let's say if I give all the queries like this only, AC, then AC, then again AC. Going from A to C is like I'm visiting all my nodes, A to B, B to C. So the query, it would be the worst case would be like every query is visiting all the nodes.
Okay, and for one query, how much it will take just for single query?
That's a worst case. If I'm visiting all the nodes for every query, it's order of n.
Yeah.
Okay.
And what about the space complexity?
Space, we have to create like map of map. So
for each node, we create. So we have n keys in the map, right? And then for each key, we have another map, which the worst case can be to every other, right? So that means that it's n squared.
Yeah, worst case, yes.
Okay. Do you guys agree?
Please repeat. Can you please repeat that worst case?
I'm saying for space complexity, if we have n nodes and we are creating a map with n keys, correct?
Yeah.
And for each key, we have another map, which is in worst case every node to every node. So
yeah,
that's going to be n squared. The space
makes sense.
Okay. Cool. Any other questions?
Quickly, we'll revisit the initial question we were discussing, right? Whether it should be adjacency list or adjacency matrix.
Okay.
And probably I'm not sure, but if there are, this is my take, okay, but you guys can edit. So if there are a lot of queries that is coming in, for example, this kind of query, AC always, if we create the adjacency matrix and then store that once we calculate, so anything that is gonna use in future, that will be really helpful. So adjacency matrix will be useful in that case.
Yeah, so shout out to who was it, Hanif?
Hanif.
Yeah,
and
so that might take more space, but at least if we hitting more queries, then it's not going to take as much time.
Yeah, and it is going to optimize also, right? So once we calculate, let's say A to C, and then there is another path A to N that goes through A to C, and we might so that over the time, if there are a lot of queries, we might fill up the whole graph, and then we will keep optimizing every query, because we keep storing whatever we calculate so far.
Yeah.
Okay.
Cool. Thanks, Vash. Any questions to add something about question 2? We can quickly then kind of cover question 3, which is parallel course. There are n nodes, which label 1 to n. So we are giving relations x to y, representing a prerequisite relationship between course x and course y. Course x has to be studied before course y. So in one semester, you can study any number of courses as long as you have studied all prerequisites for the course you're studying. In return, the minimum number of semesters needed to study all courses. If there's no way to study all courses, return 1. For example, in that case, when one course, depends. So if we actually have a loop, if course number 1 depends on course number 2, course number 2 depends on course number 3, and then but the course number 3 depends also on number 1. In that case, we can't study all the courses. So is there any questions, or do you have any idea how to proceed with this? Okay, I guess we can start explaining. Let's say in this case, right? We have 3 courses. In the example 1, we say we want to take course 1, course 2, and course 3. We see that course 1 has no prerequisites. Also, course 2 has no prerequisites out of the input, right? This course 3 depends on course 1, and course 3 also depends on course 2. So meaning that these 2 courses, because they have no prerequisites, we can take them in one semester. But 3 we have to take them in the next one because because their 3 depends on 1 and 2. So that means that we need 2 semesters in order to complete all the courses that we want. In example 2, as I mentioned before, we see that 2 depends on 1, 3 depends on 2, and 1 depends on 3. So we can't study these combinations of courses because of the prerequisites. Any questions so far? No? Anyone wants to try, or I can go directly to walking through the code. Okay, so the signature of the method, it's minimum semesters. And it takes number of courses and the relations. Okay. All right. So what we're gonna do is actually have a map for each course. We're gonna see what are the courses that is dependent on. Actually, what courses depend on that course. We're gonna have a map of integer and list of integers, and we'll name this course path, and that's a hash map. Okay. Oh, change to my language. 1 second. All right. So let me just take this out. So we have also what we need to keep track of is prerequisites. So for every course, we need to know how many prerequisites it has. So if the prerequisites for a specific course is 0, that means that that course is a fundamental. It doesn't have any, any prerequisites, so you can take it right away. So we can have an integer array of prerequisites, which is new integer of n+1. The reason why we start with n+1 is similar to the first question, where because all the courses begin with 1 and is not 0-based index. We also want to think about, so first thing we want to do is actually build the course path. So what this is going to do is going to take all the relations and he's going to build a path of it's gonna build a path, the whole course path, and then we want to know which of the courses are fundamental. So we're gonna find fundamental courses. Okay. After we find fundamental courses, we can return the number of semesters needed in order to take all the courses we want. So we're gonna calculate semesters. Okay. So let's go. Any questions so far?
Will you be doing a check for a cycle within your build course path or somewhere else?
Yes. So I'll explain later. That's gonna be when we're actually building the semester, or actually the calculating. Let me see how. Yeah, but we're definitely gonna check if there's any. Actually, I'm missing here a queue, which is which we're gonna queue all the fundamentals. Fundamentals. So the idea is if there's any If there's any course left in the queue, that means that is some kind of loop. There's like circular dependency between the courses. So yes, there is going to be check for that. I'm just so this is like the raw how we actually gonna go through the solution, and we're gonna define the methods right now.
Gotcha.
Yeah. Okay. So we're gonna drill down now in the implementation. We're having build course path, right? Now, what we need here is actually get the map of the course path, because that's what we try to populate. And then we also have prerequisites, which we also have to fill in to see how many each course have prerequisites. And we have relations, okay? So the build core path is going to be map of this. And then list of, and we have the prerequisites, and we have relations. Okay. So over here now, so for each relation, we're going to, what we're gonna do is take the course, course 1, right? Which is in this case the fundamental course, relation of 0, and then we're gonna take the course 2, which depends on the course 1, which is that's part of the relation 1. Okay. So what we're trying to say is we're trying to check now if the course path contains course 1, and we're gonna actually we have to store these store these next next courses. Next course. So if it contains, we're just gonna get that those next courses, meaning that this course has already has some next courses you can take. And once we get them, we can add this next course. And then we're gonna put the new updated list. Okay, and then also what we need to do is actually update the prerequisites. So which course am I gonna update now? Is it course 1 or course 2? Anyone?
Will this be course 2?
Yeah, correct. So the course 2 is actually the one that have prerequisites. So we're just gonna update that. So now course 2 has one more prerequisite. So this will actually build our course path. Now, next thing we need to do is find the fundamental courses. And do you have an idea how we're gonna do that?
You just look for the indexes in your prerequisites array, right? For with values of 0.
Yes, correct. So that's correct. So what we're gonna do is take the prerequisites and find the ones that have 0 prerequisite. So we start with 1, of course, because it's a 1 index, not 0. And we say that dot length. So we say that we're going to go through each of the prerequisites. So each index of the prerequisite represents the number of the course. That means, so we check now if prerequisites, the current prerequisite, if it's 0, then we are going to add the fundamental. Add as a fundamental. Is it clear so far? Any questions so far? No. Okay, so I'm gonna go through. So now that we have the fundamental courses, we are going to we're going to actually calculate the semesters. In order to calculate the semesters, we will need we'll need to have all the data structures we use so far. So we will need the course path. Okay, we will need the fundamentals. We will need the prerequisites, and we will need also the number of courses. So yeah, so we're gonna take the course path. And then we're gonna take fundamentals. And prerequisites. And number of courses. So first, we're gonna say that. So we're trying to go through each one for the fundamentals. So we're trying to go one of the first courses that we can take for the semester, and then we just gonna go down until the last course. So while fundamentals is empty. Okay, I'm sorry, it's not empty. We are going to say that get the number of courses that are fundamental. So for each of the fundamental, we are going to we're gonna get from the queue. First of all, let's not forget this. Once it reaches 0, means that we covered all the fundamental courses. So we're gonna get the course of fundamentals. So Paul is going to just return the next fundamental. We're also going to decrease. This means that actually, look at it this way. This means that we actually taken the course. Now we have n-1 course to take. So if the course path contains a course, then we're going to get all the next courses. Okay, And then for each of the next courses, we're actually trying to find if some of them is fundamental. Next course. So for each next course, we're gonna take it from the prerequisites. Since we remove this, remove the previous, so we're taking this course, let's say we take course number 1. So all that depend on course number 1, we are going to minus it. And then if some of the prerequisites do not have a course that it's a prerequisite, I mean, if all the courses not next do not have any more prerequisites, we can consider that as now as a fundamental. So, okay, so we have number of courses. Oh, yeah, and also we need to calculate how many semesters. So we have here semesters. We start from 0. So for each, so every time we take a fundamental, we can, every time we have in a certain, let's say we have 5 fundamental courses, that means there's no limit how many you can take. So I mean, we can put them in the same semester and return semesters. Now there's another thing we need to check is if, let's say, if we haven't taken any course, means that if there are still courses to take, that means some of the courses depend on each other. So we can just, which means we can't take all the courses, set of courses. So I hope I was clear enough. If is there any question about this? Anything I can clarify further?
So is this kind of similar to like topological sort doing it in BFS? And just like adding that semester, incrementing semester whenever we complete one cycle of queue?
Yeah, so can you repeat that again? If so yeah, we are incrementing the semesters in this example. For we see that 1 and 2 are fundamentals because they don't have prerequisites. So we put them in the queue, and then for each of the, we know that these can be taken in 1 semester. So that's why we increment that semester. Now, when these are taken out of the queue, then this does not depend on any other. So now we go to the next level, and then that's the semester 2 actually. Is that answer your question, or you're expecting something else? You asking something else?
I'm just saying, like, this is like, this implementation is like similar to the topological sort implementation in BFS.
I think so, right? Because he's
Yeah.
creating the graph first, and then he's disconnecting the vertices without any,
Yeah.
I think, connected to them, right? And then moving on to the next layer of vertices that have no edges connected to them.
Yeah, it's only the tricky thing is like, when to increment that semester. Yeah.
Yeah, so you increment that semester once you are going through the queue. Let me see if I can do this. Oh, sorry. No, not that. Okay. So here is going to be, 1 second. So the queue initially is going to contain, sorry. the queue initially is going to contain 1 and 2, right? So this is, so the queue is going to contain 1 and 2. So we go for each queue, and then we take the prerequisite for this and we decrease it. So we take course number 1. I don't know what happened with this. So we take number 1 and then decrease the prerequisites for 3. And then we take number 2 and then we decrease the prerequisites for 3. So first 3 starts with 2 prerequisites, and then it goes 1 prerequisite, and then it goes 0 prerequisites. Now, when we cover the 2 courses, that's when we increase the semester. So semester +1 when we go this. And then, so this is gonna be 1 semester. And then when we come to course number 3, there's no other fundamental course, then there's no other courses that don't have prerequisites anymore. So it's 1 note. So that's why we go to semester +1. So that's gonna make it 2. Is there any does anybody can explain better in more clear?
So I think it's when you, so tying it to sorry, I don't know who spoke, but tying it to the topological sort, it's when you add, so you add all the initial vertices that don't have any prerequisites in this case to your queue, and then whenever you clear it out, that's when you add a new semester. It sounds like.
Yeah. So when you queue, when you actually take out from the queue all the courses, that's when you increase the semester. Meaning taking the courses in real life.
Mm-hmm.
So taking out a course from the queue means kind of like taking the course. Is that clear?
Yeah, I think so. It's clear. Yes.
Okay. So what is the time and space complexity for this? Can anybody tell me?
Before we go there, where are we just checking the cycles, and if there are cycles, we should just terminate?
Yeah, the cycles are right here. So when the number of courses in this case, let's say fundamentals.
So I think
If the
when there are
prerequisites,
cycles, the prerequisites will not be 0, I think.
yeah, when there's not 0, that means that this course depends on someone else. So that means that it is not going to be added to the fundamentals. So next time the fundamentals.
Got it. So basically, you are reducing n every time a course is kind of studied. So
yes.
When the external while loop is exited, you're checking if n is 0 or not. If n is not 0, then okay, got it.
Yeah, correct.
So for the second example, the find fundamental courses will not add any prerequisites, correct?
Where's that?
For the second example, so when you're calling the find fundamental courses, so adding initial prerequisites to the queue, so that will not add anything, right?
In this one, right?
Yes.
No. In this one, it is gonna add number 1. Actually, let me see. So we're gonna find fundamentals. Yeah, it's not gonna add to the queue, correct?
Okay. So that means like initially it picks like whichever the node has in degree 0.
Yeah.
Okay.
Any other question?
I have a question. What if the each course is not cost 1 semester? For example, example 1, maybe the course 1 spent 2 semester. What to deal with this situation?
Can you can you repeat that? I'm sorry, I didn't get it.
What I mean is, what if the edge course is not 1 semester? maybe the course 1 spend 2 semesters and course 2 spend 3 semesters. Well, how to deal with that situation?
So if course 1 is taken multiple semesters, you're saying if it's
Yeah,
long
yeah,
enough?
yeah. Maybe 2 semesters and course 2 spend 3 semesters. Yeah. In this question, each course spend only 1 semester. That means the edge course is equal to 1 semester. Yeah. Well, what if the edge course is not equal? How to deal with that situation?
Well, in that situation, then we're gonna have kind of like a weight for each of the nodes. So we're not gonna take course until, let's say, course 1 is taken. Let's say if course 1 needs to be taken in 2 semesters, then we kind of like we have to put it back to the fundamentals queue until this weight is 0. I mean this until the semesters left are 0. So we can have another kind of instead of prerequisites, we can have another array that's gonna is gonna say how many semesters this course needs to be taken, and if the course has more than 0, that means it's gonna be put back to the fundamentals queue until it becomes 0. Then when it's taken out, it's gonna continue as it is right now. Is that clear?
Yeah, I think maybe in the calculate semesters, we have to change the semester calculation. It's depend on the course, the mental pole, the course, and depend on the edge weight, and that edge weight to the semester maybe. Yeah.
I'm not sure. Can you if you want, I can give you a remote control so you can actually, if you want to draw it out.
Not necessary. I just met this problem in my interview. Yeah, that question is similar to the parallel courses, but the requirement a little bit different. Like they have a different edge weight, and when I answered that question, I was not sure, so I asked the question here.
So you're not sure how to actually deal with a course that can be, so it should be taken in multiple semesters, correct?
Yes.
Yeah.
The edge is not equal. It's different edge weight here. Yeah. Thank you.
Yeah, no problem. Yeah, so that's a way to go. Like until you're gonna add it back to the queue until actually it's complete. If anybody else has other suggestion of how to solve that, they can share it.
I think this is Vivek. Quick thing here, right? So I don't think you should say that it's the edge weight is 2, because I think it's like it's the course that actually.
No, the course weight. Yes, I meant
the
the course weight.
has, so the node has a weight along with it, which is like the value, right?
Yeah.
So the way I would do it is essentially, I mean, you're saying it's 2, but it's not necessarily 2. It could be 2, 3, or even 4 semesters long, right? So there will be a number, and you will be just decrementing that value every time, and then you will keep it in the in your queue till it goes away.
Yeah,
right?
similar to prerequisites. Let's say we have another array that will handle.
No, it's the same queue. Just use the queue itself.
Oh, it says yeah.
When you actually on the queue, what you do is that if it's 0, then you just do that. What you do is just take it and you just throw it out. If it's non-zero, then you subtract 1 and then you put it back.
Yeah, but in that case, we need to have some data structures, which will say course, and then the course weight. And it's not going to be just integer, correct?
Yeah, the course will be like a data structure, which is number and weight, or like or something like that, right?
Yeah, correct.
Fair enough.
Yeah. All right. So what is the time complexity for this? Can anybody tell me?
maybe linear because every node we visited, poke it up and put it to the result. I think it's O of n. N is the number of the node.
Okay. Yeah, anybody has any other opinion about this?
What if we have a like 1 depend on 2, 2 depend on 3, that kind of graph? Do we go, that is up to 10, do we go multiple times in the same loop? Say that first time we go for 8 times, second time we go for 7 times, then 6 nodes, then 5 nodes. Does complexity change? Since we have a multiple loop right here.
I think we are checking for
No,
integrity, so I think
yes.
we'll not go into the loops.
Yeah, it's not gonna.
So let
So
me
first, if
No.
it's 1
what
to
if-
2,
So let me ask a different question then. What if every course actually depends on multiple courses before it? So for example, 2 depends on 1, 3 depends on 1 and 2, 4 depends on 1, 2, 3, and so on.
Exactly.
Then the number of times you'll have to go through this operation is actually
so
right?
say it again. How was it? If 1 depends on what?
Every course depends on all its predecessors. So 9 depends on 1, 2, 3, 4, 6, 7, 8.
Can you draw that out?
I mean, every numbered course will depend on all the numbers before it. So 1 depends on nothing, 2 depends on 1, 3 depends on 2 and 1 both.
Oh, okay. You mean like, okay. So,
Other way.
okay. And then 4 depends on
1, 2, and 3.
And 1 also, yeah.
So that means you have to take 1 first, then you have to take 2, then you have to take 3, then you have to take 4, right? That makes sense. But
Yeah.
in this case, the complexity of this operation is not number of courses. It's actually V plus E, number of vertices plus number of edges, because you have to resolve every edge, right?
Okay, so I guess you're gonna take 1 first, right? And then the next one you need to take 2. Okay. And then 3, right? And then 4. So you're
Correct.
saying 4 edges? I mean,
What's
4
the
nodes?
Whatever you just did,
Mhm.
it's not O of n, right?
Okay, so it's O of number of vertices, which is 1, 2, and 3, 4, number of courses, and the edges.
Correct. It's V plus E, number of vertices plus number of edges.
Okay.
Can we quickly look at the code? Basically, I want to see if so first while loop, right?
When we are right here, right?
Yeah. So first while loop will basically
Going to have 1 course in this case, what we just
yes,
discussed.
yeah, and then the inner while loop. We go through
the number of courses are in the queue right now.
Okay, so first we have all 10 courses, right? Oh no, 1.
No, we have 1 course.
Okay.
In the case we discussed, we will have 1 course each time.
No, I'm talking about the inner for loop, last for loop.
Oh, the last one.
Yes.
This one.
Yes. So basically we go through all courses.
Yeah.
And then if the course.
But we go through every course only once here in this.
Yeah, but then you need to go through all the prerequisites.
Yeah.
So
I'm thinking that it is not only wedge and edges, but it is a little bit more than that.
Yeah. So you're saying that in that case would be n times n
squared.
Yeah, the worst case. That's true.
Yes. Yeah.
But why are we doing it? I think that that's the algorithm that you're using here. But why are we actually going through all the courses?
No, that's in worst case. We don't need to go through, depending what's given.
No, but you are going through all the in the inner for loop, right? Oh, you're going through next courses. Got it.
Only the next courses, yeah, not through all of them.
Makes sense. So that will be V plus E, right? The next course is the edges.
The next course, no, the next courses are the next nodes. Let's say for 1, the next node is going to be 2, or for 3 is going to be for 2 is going to be 3. In the case we drew before, the next course for 1 is going to be 2, 3, and 4. The next course for 2 is going to be 3 and 4. For 3 is going to be 4. Get it?
Yep, I understood that.
Yeah.
But then
Okay.
what you're doing is that you're going through that list, and every time you go through this, you're actually eliminating one edge, right?
Yeah.
The next.
Yeah.
Every
Yeah,
aspect.
Yeah, that's true. That's true.
It's
Yeah.
not an iteration, not the entire for loop. An entire for loop will eliminate like n number of edges, but each line of each entry in the for loop essentially is eliminating one edge. So once you're done with the entire algorithm, you would have gone through the inner for loop precisely edge number of times.
Okay. So it's gonna be.
It's v plus e.
V
I don't
plus
think
E.
it's more than that.
But no, why V plus E? Why is not V times E? Because we're going through every vertex.
But once you have eliminated it, are you not eliminating that going once you're done with one, you're looking at all the nodes that are connected to one, and you're done with that. Then next time you come, you're looking at 2 and all the nodes that are connected to 2, and those are different edges, right? So I don't think it's V times E. It's just V plus E, right?
Okay.
Like every step, you're only connecting. You're eliminating one edge, and you're never eliminating the same vertex twice, same edge twice. Since you're not operating, you're not even looking at the same edge twice. You are only going through the edges only once. So the inner for loop will never run multiple times for the same edge.
But do we go through everything to check whether they have edge or not?
We don't, right? That's a part of the elimination that goes away. When you do the next course, you're eliminating all the nexts of 1, then you're eliminating all the nexts of 2, you're eliminating all the nexts of 3. So you'll never go back.
So when we do 1, we basically say that all are eligible next, right?
Yeah, we take 1, and then for each of the courses, we decrease of the prerequisite. It means that we're taking this course out of the picture.
So we're just taking 1 out, right?
Yeah. And now we check which one of these. Now, if every time we remove one, we remove edge, we check whether the in degree or means prerequisite of the current course is 0. When it's 0, we just put it next to the queue. So now this one is gonna be in the queue.
Okay.
Yeah.
Basically, 3 cannot go because it still has a in degree of 1. So basically, we are checking the in degree. What is my current in degree left?
Okay, so in that case, what if 1 is dependent on 2, 2 did? So basically, if there's a linear.
Then there is a cycle. I think that's what he told. We will
No cycle. No. I'm taking the straight line. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
Okay.
In that,
basically, like this?
Yeah,
Okay.
exactly that. So in that, basically, when we do 1, we gonna check all 9 whether they have 1 or not, right?
No, we're only gonna check number 2, because that's the next one.
I see. Okay.
Yeah.
Its neighbors.
Okay.
Yeah.
It will go to all its neighbors and try and remove 1 in degree, telling like I'm done with my edge. And then if that neighbor ends up having 0 in degree, then we can put that in the queue.
Yeah. Otherwise, so this one's gonna go in the queue.
Otherwise, when it will come from some other path, that time its in degree will become 0, and then that time I'll put in the queue. So basically, think that it is a in degree, and once the in degree becomes 0, it is a candidate to go in the queue because nobody is dependent on that.
Yeah, actually, this is gonna be the best case.
Yeah, perfect. Yes. Yeah. One more just twist to add. What I think Vivek also told me. The other twist is to this problem, right? So here we are saying that whatever the maximum semester you can. I mean, if suppose there are 10 courses, you can take 10 courses. There's no limit to how many courses you can take max per semester, right? What if we add that limit? How this problem will change? For example,
what?
we had a limit saying that per semester you cannot take more than, let's say, n course, let's say 3 course or 4 course.
Okay.
And if we have that limit,
Okay.
and then we have to find, optimize semester.
Got it. What can we do when? I mean, I would say. So does anybody else have an idea?
So when you are going through the courses, right, the inner for loop, I think you'll need to add a terminal condition in there that the max courses per semester, if you go back to the code, the max courses per semester, no, not here.
The above method.
Above.
Yeah.
The inner for loop here, right? Here, in addition to going through all the courses, you'll also add a decrementing counter, right? As soon as the counter, which is the max number of courses per semester, you need to break out, right? Then your prerequisite.
But you can do. I think you'll need another queue now that's gonna say, let's say we find fundamental courses, right, that don't have prerequisite, and the limit is, let's say, 1 per semester. So 2 is gonna be kind of like left hanging. So what we maybe will do is, once the fundamental is empty, we check if there is any queue with other fundamentals that could not be taken. Then we just take them from the queue until fundamentals is full, and we do it again. Does that make sense?
There's a reason why that won't work, right? The challenge that you have is there's no bias in your algorithm that actually will pick course number X versus course number Y. If there are no prerequisites for the 5th course and the 6th course, and you can only accommodate 1 course in the current semester, which one will you pick?
Yeah.
That should depend on which actually has dependency. Like if 5 has no dependency, nobody depends on 5, and a bunch of them depend on 6, then you should do 6, not 5. Right?
Yeah. Oh, yeah, that's true. That's correct.
You got to think a little ahead in terms of who depends on me as well. Like whom do I depend? So there's a little bit of, it's quite tricky. I mean, I don't know whether we want to go through the thing in detail here.
Yeah, I'm just throwing the question. I mean, it won't be that simple as just limit, because out of suppose course X has a 10 dependent, right? And we can just release only 5. We can't just randomly choose 5, because that won't give you optimized algorithm. Because because let's say that course 1, for example, course 1 it's done, and then there are 5 dependent course, but we at max you can take only 4, right? Now in next semester, if you randomly choose 4 and left the 5, right, and you left the course, all other courses are depend on that. So next semester you can't take any other course, because the dependent course is left. So we can't optimize for parallelism there.
Maybe we can have some kind of priority queue when we just assign.
Yeah, depend on how many are. Yes.
Yeah, how many dependents?
How many depend on that? So whoever is dependent more, we can take and think. Yeah, so it will be a little bit involved.
Think a little harder, because I don't think that the priority queue priority is not based on the number of courses that depend on me, right? It could be that you could be on the. So this is essentially you're doing what is you're essentially trying to figure out the critical path.
Yep.
And you're essentially putting the critical path, and then you're trying to figure out. The parallelism can be handled afterwards. So one thing you can do is you can do a topological sort and identify the critical path, and then make sure that you prioritize the critical path up front. And then once you eliminate the critical path, you actually have like this next critical path and the next critical path and so on. So it's not an easy answer. The only reason why we bring this up here is that like this parallel course question is very common graph question, which is often asked in interviews. And some of these extra things are the complexifiers that are added on top. If you finish the question fast enough and on time and everything else, then the interviewer will actually ask you something about like, hey, what about this one? Now you should have deliberately, like you should have thought about it. You should have have at least an approach to solve it. You don't necessarily have to solve it. Like, I mean, you can't solve all the variations, but like, making sure that you are at least aware of these changes or these differences. And how are you reasoning about it? Not just memorizing this answer of saying this is how topological sort works, but actually understanding how we have arrived at this will help you be a lot more competent in answering any of these extra questions. Anyway, but good variation though.
Yeah.
So what is the minimum? So what's the complexity? The time complexity? V plus E. Like, can this be ever done when O of n? O of
No
V,
way,
sorry.
right? You have to resolve all the edges and you have to visit all the vertices at least once. If your algorithm is efficient, the minimum you have to visit everything once, right? You have to go through all the edges and delete them, and you have to go through all the vertices at least once.
So it's O of V plus E because of the fundamental courses, because we are building that adjacency list. It's not because of the calculate semesters, right? I mean, just looking at
even during calculate semester, you're going through all the edges and all the vertices once.
So
Imagine you are given the.
Let me add a variation. Let's say
even if you're given the let's assume that you're given this count, the dependency count, you're given all the inversions, matrix, and everything else, right? Even then you'll have the exact same thing because you have to go through each node once and you have to go through each of the vertex once, each of the edges once. But go ahead.
No, not necessarily, right? So let's say if we choose a simpler, let's say there were no cycles. Let's assume there was no cycle, right? Then you don't necessarily need to go through each edge. You basically have to build an array where what is the number of integers. And if you were to keep that array sorted somehow, let's say in a min heap or something, you just need to pick the one with the least degree, evict it out, and reduce the degrees of everyone else. Then you are just operating on the number of degrees.
Can you repeat that line? What do you mean by
so
everyone
let's
else?
say let's take the example 1, not the example 2, but example 1. So you're getting this inputs as 1 pointing to 3 and 2 pointing to 3, right? So you say 1 has length of not length, one has in degree of 0 and 3 has in degree of 1. Then you come to the 2 pointing to 3, you say 2 has in degree of 0 and 3 has in degree of 2, right? So you're building a map of the node and its in degree, and you're also building a reverse map of in degrees to the courses, right? So you have two maps. One is the node to in degrees. The other is an adjacency list of in degrees to the courses, right? So then you say, oh, I'll start with 0 in degree, finish off 1 and 2, and then I'll go to the in degree of 1 and finish off 3.
No, hang on. So when you finished off 1, what did you do? You reduced the in degree of 3.
Actually, I don't know even if you have to worry about reducing the in degree, right? Because
if you don't do that, how do you know that 3 is now open?
Because you're going in sorted way.
On what basis? Like, let's imagine you had the same thing, but you had like another one, which is like, let's say 1 dependent on 3 and 2 dependent on 4. Like, let's say we had something like that, right? It was not like, it's not 2 and 3.
Oh,
1 points to 3 and points to 4. Now, at this point of time, 1 and 2 are actually of in degree 0, and 3 and 4 have in degree of 1. Correct?
Okay. So then
now,
when you're in your in degree data structure, right? In your 0th one, you'll have 1 and 2 listed as with in degree 0. You'll complete them. And then when you come to the...
Let's not complete 2 yet, right? So at this point, let's actually... Fine, so let's do that. Actually, you know what? Why don't you draw this? Can you draw 1 pointing to 2 or 3
Okay.
and then 2 pointing to 4 independently? Okay.
Right. So now
and can you also draw just below that? Can you draw 1 not pointing to anything? And then no, not 5, just 1. I want another problem space because the answer for these two will be similar.
Okay, you mean another graph?
Yeah, just another graph, brand new graph. Yeah, just do 1, just 1 not pointing to anything, and then 2 not pointing to anything, 2 pointing to 3 and 2 pointing to 4. And 2 pointing to 4, and then 3 pointing to 4 as well.
3 pointing to 4. Okay.
Okay. So let's go.
Okay. So there are two data structures. One is keeping count of node
So in this case, in degree of 1 is 0, in degree of 2 is 0 in both graphs, right?
Yes. Yeah.
And which one will you pick first, 1 or 2? Doesn't matter.
It doesn't matter.
You picked 1. Actually, can you delete the line between 2 and 4 in the second graph? Sorry, I missed that incorrectly. I added that. No, the second one. Thank you. Okay, so now you've resolved 1, you resolved 2. As a part of this, what is the next step? How do you know that 3 and 4 are open now?
Yeah, because both have 1.
Okay, in the first scenario, 3 is, in the second scenario also both have 1. In the first scenario also both have 1. But in the first case, once you've solved 1 and 2, 3 and 4 both become open and available. And the only way you do that is by actually traversing the edge.
So, okay,
outside.
okay, yeah, okay, let me address that. So basically the information that we need to carry forward when we are building the degrees is how many are my ancestors, right? So when you build 2 to 3, you say, let me take the degree of 2 and add a 1 to it and put that as the degree of 3, right? So degree of 2 is 0, right? Nothing is incoming. Degree of 3 is 1 because it's 0 plus 1.
Both graphs same value.
I'm looking at the second example.
But both graphs, like whatever you're saying, tell me if there's difference between 1 and 2.
Yeah, there will be, right? So, okay, let's focus on the first one, 1 pointing to 3 and 2 pointing to 4, right? In degree of 1 and 2 is 0.
Correct.
Right. Now you come to in degree of 3, you say, oh, let me add my in degrees of my ancestor, which is 0 plus 1. So in degree of 3 will be 1. Let's not call it
you're adding in degrees of your ancestors.
Yeah, you just have to carry on the information,
right? You'll have to give me some more time to come up with an example where that will fail.
Sure.
So, I mean, you're just trying to come up with a clever
as long
way
as
to
there's
figure
no
this out.
cycle, I think this might work.
I don't think that is, my intuition says that's not right. So the way I'm looking at it is that the sanest way to look at this is to say that the fact that you have an outbound edge from 1 is why you're actually reducing the in degree of 3 and you're actually making 3 available. In the first case, and in the second case, only after you resolve 2 can you make 3 available, and 4 will not be available till 3 is resolved.
Sure.
That's how it works. That's a pretty straightforward way of doing it.
Sure.
I don't think there is any clever way by which you can, even if you did like an insane amount of pre-processing and you calculate everything and keep, right? There is no good way for you to figure out.
No, I mean, basically you're accumulating information, right? As you're going down the path.
But if you have like
I can actually give you an example where it will fail.
in degrees to 3, maybe it becomes challenging.
What's that?
No, I'm pretty sure I can come up with an example where the specific enhancement of the algorithm you did will fail.
Okay,
fairly confident, because I think there is no good way for you to identify this. This information cannot be condensed. Like you have to have this information like available in the raw at a time you're resolving every node. You should have the answer to what that looks like, because
I think the information is captured. What I think your concern is the information captured because you're also spending time in keeping the data structure sorted. Like you're not just randomly picking up, can I now do 4? You're keeping, okay, now where I am, which are the nodes which has the least in degree? Let me finish them off.
So in your example, okay, let me actually maybe go there. So in your example, would the value of 4 in degree of 4 actually be different if I have an edge between 2 and 4 or not? Will the value of 4 be different if I have an edge between 2 and 4 or not? Based on what you said, that simple algorithm, there should be a difference because you're adding all its ancestral values, right? So you'll count 2 twice for 4. Once because it's cumulative for 3, and once it's because coming from 2 directly.
Okay. Okay, so is that matter though? You are not dependent on on that value, you're just dependent on the order.
Correct, but if something is double captured, then I think if I sufficiently engineer the system, I can mess, right? Like I'll have to draw a slightly larger graph for you.
Yeah,
and I have to add the connections in such a way. So the 2 to 4 connection is actually spurious, right? That connection or not does not change the topological sort order. Yeah, something like this. Correct. And,
Okay.
and then I might actually add an extra spurious edge between 2 and 4 directly or something else and add like 1 more or 2 more things in between. The concern that I have with this is that you wouldn't know whether you need to run like the
okay. Yeah. So the
collapsing
concern,
or
yeah. So the concern here
accumulating
would be,
values will actually completely mess with your thing. So I think
concern here
while
would
it's
be that you
clever,
might delay taking 4 for a longer time.
correct. Whereas you
based
could have
on the
taken 4
ordering.
anytime at this point. Anyway, so
Yeah.
good
Unless,
exercise. I think it's
yeah.
definitely helpful. I think the thing I want to go back and reiterate is that in this particular for this particular algorithm, it is typically always like it's edge number of edges plus number of vertices, primarily because that's how you do it, right? You're resolving all the like vertices as you go through the order, and then you are making sure that you're going through every edge once and you're eliminating that edge or you're resolving for that edge, and that's why it's B plus E. And I don't think there is any way around it, even if you kind of like accumulate a whole bunch of things up front. Like you do a bunch of calculations, reversing, like A to B mapping, B to A mapping, inversion of maps, do all of that. Still, I think you'll have to go through this exercise. I mean, I don't think there's any way you can make this happen.
Yeah, even if you are building the reverse maps, you are still going to spend 1 computation cycle to adjust the weights.
Assume that is like amortized, so that's free. That's not counted, right? Even given that that particular thing, the pre-compute is not counted, the actual traversal will take B plus E, is what I'm saying. And I don't think there is any way by which you can actually like counter that. If anyone has an algorithm or an approach, we can engage. Let's chat on the Slack, and I'm happy to walk through the algorithm and probably come up with an example where it might fail. All right.
Okay.
But great exercise, great thought. It's good. Love the discussion. Back to you, Martino.
Thanks. And it will be nothing with you guys. So, yeah. Any questions before we wrap up?
Actually, I had one question. Like, has anyone faced any of like similar questions in real interviews anytime? Like in the recent past or otherwise, like, or heard of someone talking about it? You don't have to mention the name of the company, but just wanted to hear from people if they've seen these questions being asked, because I think in my experience, like at Amazon and other places, I've actually heard these questions at different points of time. Typically, I've seen graphs being used more commonly, and usually it tends to be like simple traversal, like the town judge example, or the like topological sort, or DFS BFS variations. And I've seen that a lot, very often. So I'm just curious to see if people actually had seen interview.
So you mean to say advanced graphs are typically not asked? Is that what you are trying to judge?
I don't think that. I mean, it's like even Dijkstra's, I've not seen that asked like that in that particular way. I mean, the question will be presented in such a way that the answer might be to do a Dijkstra-based traversal or something like that. But invariably, it ends up being like, you can derive it from first principles to some extent, and even come up with like a semi-optimal or slightly suboptimal solutions. And so typically, I've not seen. I don't know. Maybe Google or like interviews at Facebook or some other places might go a little deeper. I haven't. I'm not privy to that. But
yeah, I tend to agree with that. Yeah.
I haven't seen people go too deep in this. They generally expect, because you're expected to code as well, right? It's just harder to code some of these things beyond a point. So any feedback on what people have actually experienced in real interviews?
So I have heard about the second problem in different format, meaning to say currency exchange type of problem. So
yeah, Roger mentioned that in the chat as well.
Yeah.
Good, thank you. And I think there is a link in the comment. And Roger, if you don't mind, can you post that back in the chat in the Slack as well, because that stays longer, and folks can definitely refer along to it.
Sure, I will do it.
Thank you.
Thank you.
Thanks, guys.
Thank you.
Thank you.
Awesome.
Bye.
Thank you.
All right,
Yeah.
that's all we had, I think, for today. Thank you so much.
Thank you.
Thank you, Mario.
Thank you. Bye.
Thank you.
Thank you guys.
All
See
right,
you
bye-bye.
next weekend, or maybe every
Tomorrow.
morning.
We have daily sessions too.
Yeah,
Yeah.
Oh,
All right.
really? What time is it?
8:30 in the morning.
8:30 PST, and
And
that is actually for lead code questions. So join the lead code channel, and you can join us on the discussions.
Tomorrow it's 9.
Oh, tomorrow it's 9. Okay, sorry.
Every Sunday it is 9.
Got it. I should update my reminder mail.
Mhm.
Thank you.
Awesome.
Thanks.
Thank you.
Bye.
Thank you guys. Bye.